Good day, everyone. For today, we will going to present to you our proposed project proposal, which is entitled the Solar Power Water Irrigation System with Mobile Application, together with my group mates, Delan Janalea, Nire Maria Christie, and Udin Shan. So for the background of the study, in the current global context, farming is having a hard time because of climate change and not having enough resources. So people comes up with new ideas to make farming more sustainable. One cool idea is using solar power for watering the crops and using a handy app to control it. The study looks at how well the solar powered system works to help farmers deal with challenges and be more eco-friendly, especially considering the problems we face with the changing climate around the world. So for the statement of the problem, first we have not having reliable and affordable ways to water the crops. Second, inefficient water usage and spending too much money with old-fashioned watering methods. And third, farmers can't easily monitor and control when they water their crops in real time. Okay. So for our objectives of the study, the primary objective of this research is to examine if the solar powered water irrigation system with a mobile application is practical, cost effective, and eco friendly in a specific agricultural setting. The goal is to improve sustainable farming practices locally and contribute to the global effort against climate change.
For the significance of the study, the solar-powered water irrigation system with mobile application has a lot to offer stakeholders in technology, agriculture, and the environment. Increased irrigation efficiency, lower expenses, and remote control using a mobile app are advantages for farmers. By lowering greenhouse gas emissions via the use of clean solar energy, the technology supports sustainable agriculture. It provides it will provide developers with a platform for technical innovation. Insights can be used by policymakers to encourage sustainable irrigation, supporting more general agriculture and environmental objects. For the scope and limitations of the project's main goal is to create an irrigation system that runs on solar power and has an easy to use mobile app to maximize water use and boost agricultural output. It investigates the advantages for the environment, economically viability, and technical feasibility. Reliance on farmer adoption, economic constraints, and geographical solar variability are among the limitations. The usefulness of the mobile app could be impacted by smartphone accessibility and connectivity. The project understands that it cannot solve every issue and that it must be flexible enough to work in a variety of agricultural environments.
So for the chapter 2, conceptual framework, the goal of the project is to improve farming methods by using a mobile application and a solar-powered water irrigation system. While the app allows for remote monitoring and control, provides real-time weather and soil moisture data. The system guarantees dependable energy for irrigation. The theoretical framework applies big data concepts to optimize agricultural practices through data-driven decisions. Solving water scarcity concerns for sustainable farming, it draws from system theory, emphasizing the interconnectedness of the system components. So empirical studies, current empirical research emphasize how mobile application and a solar power water irrigation device can increase agricultural sustainability and efficiency. So particularly, evaluation of a solar powered irrigation water with remote monitoring and control, written by F according to O. Oyedeli et al. A system like this might increase agricultural yields up to 30%, decrease water usage up to 35%, and save energy up to 50%. When combined with a mobile application, these results were obtained in Nigeria. The study placed a strong emphasis on data-driven decision-making, user happiness, and ease of use. All things considered, it offers empirical proof of the efficient and solar-powered irrigation system with a remote monitoring and a control resolving agricultural water scarcity issues.
Okay, so for the 2.3 synthesis of previous researches, the studies by Jabbar and Ramli 2002 and Ashutosh et al. 2006 both explore a solar-powered irrigation system with IoT integration to improve agricultural practices. So the key themes include sustainability, solar energy utilization, and IoT for real-time monitoring. Both emphasize user-friendly interfaces accessible through smartphones. Jabbar and Drumley use the Blink to IoT cloud for data transmission, while Ashutosh et al. Focus on an Android-based application. No explicit conflicting findings are identified, but potential disparities may arise from variations in system performance, adaptability, or user satisfaction, and it influenced by factors like technology advancements, geography, or evaluation methodologies. A more detailed analysis and direct performance metric comparison are needed to unveil any conflicting results. For the gaps in the IT literature, in the existing research on a solar-powered irrigation system and IoT solution enhances agricultural practices, but studies lack explicit gap identification or comparative analysis. Jabbar and Rami introducing an accessible IoT or SIS with a solar-powered portable water pump, focusing on user-friendly smartphone interface and IoT for real-time monitoring. So similarly, Ashutosh et al. 2016 introduced an Android-based solar-powered automatic irrigation system, emphasizing environmental sustainability and user-friendly interface for real-time soil condition data. Both studies contribute by filling identified gaps and advancing understanding of solar-powered irrigation systems and IoT applications in agriculture. So for our chapter 3, the methodology, we have here the requirements gathering and analysis. And first is 3.1.1, the research local. So for our research local is that integrates a solar power water irrigation system with a mobile app in both Bukidnon's rural landscape and selected urban areas. So why Bukidnon? Bukidnon is known for extensive agriculture, serve as a practical setting to implement this technology in traditional farming communities. Rural areas highlight challenges and opportunities for farmers using conventional irrigation, while urban areas offer insights into adapting the system for smaller scale urban agriculture. So this dual approach captures diverse socioeconomic and environmental contexts, essential for assessing the system's adaptability and scalability in mobile both rural and urban agricultural practices. So for other respondents of the study is that the researchers' instrument based to evaluate the adoption and effectiveness of a solar-powered water irrigation system with a mobile app involves a comprehensive survey and interview process targeting farmers. The questionnaire focused on the assessing farmers' perspective on usability, effectiveness, and economic viability of the system. It explores aspects like mobile app user friendliness, impact on crop yield and water conservation, maintenance requirements, and overall satisfaction. So for the interview supplements, they survey by providing deeper insights into farmers' experiences, challenges, and suggestions for improvements, offering a nuanced understanding of the system's practicality and potential for widespread adoption in agriculture. And then for the research instrument is that this study targets farmers instead in a solar-powered water irrigation system integrated with a mobile app. The respondents are agricultural practitioners seeking efficient and sustainable irrigation solutions. So the sample includes farmers from diverse geographical location, crop types, and land sizes. Using a stratified random sampling technique, participants are proportionally selected from various farming demographics, ensuring representation across different regions, farm scales, and crop varieties. So this approach aims to provide a comprehensive understanding of the system's viability and usability among a diverse farmer demographic.
So for the system design, system architecture, so the solar panel, they convert energy from the sun. direct to the current, and then ang direct current mo na din ang i-convert sa solar into AC or alternative current. Tapos ang battery dayon i-store, tapos battery dayon ang energy mo kuha dayon sa RPI. Energy gikan sa battery dayon serve as a main controller sensor. So the sensor din sensor, ultrasonic sensor, and sa moisture dayon. Tapos ang relay is connected siya sa battery kay kinahanglan gyapon siya electric switch man, tapos kay ang switch is need siya electric energy para ma-turn on, and dayon ang user na og ang smartphone para ma-detect og mag-monitor and mag-process sa system.
So for our ERD, we have here the two fundamental entity, the farmer and the watering system. So the farmer has its own attributes, the name attributes and the farm attribute. Since the farmer, it has its own name and own farm. And then with that, the farmer will be the one that will monitor and the one that will gather data in the watering system. So these two entities are called associative. And then from the watering system, it has its one attribute, which is the crop, since the watering system will be used to water the crops.
So for the use case diagram, and this is the farmer, he or she have to log in or log out, and connected saya ang kuan kay naman siya mobile app. So mo na mong use case na siya monitor sensor data, control irrigation schedule, receive notification, adjust irrigation settings, and napod may kaning taw-taw diri nga sensor system. So mo siya ang mag-collect og data, and the irrigation system mo siya ang mag-control sa irrigation system.
Okay. So for the context diagram, we have our proposed project, the solar-powered water irrigation system with mobile application, and the entities are the external environment, mobile app, and solar panels. So for the external environment, it represents external factors such as weather conditions, soil conditions, and other environmental variables that influence the irrigation system. And the external environment does not interact directly with the system, but provide input through sensors. So after the external environment, we have the sensor data. The sensor data, various sensors collect data on soil moisture, sunlight, and weather conditions from the external environment. So this data is transmitted to the solar power water irrigation system for analysis and decision making. So the solar powered water irrigation system is the core system that processes the sensor data, controls the water pump, manage the irrigation schedules, and interacts the solar panels. And also, it makes decision based on environmental data and user-defined schedules. So the mobile application allows users to interact with the system, providing a user-friendly interface for monitoring the system status, setting irrigation schedules, receiving notifications, and also the user interaction. These user interactions, users can set and adjust irrigation schedules based on their preferences using the mobile application. And the third entity is the solar panels. The solar panels generate power for the system to ensure sustainable energy for its operation. So for the data flow diagram level 1, we have here the external environment, which has the soil moisture, sunlight, weather condition. This represents external factors such as, weather conditions, soil conditions, and other environmental variables that influence the irrigation system. So next for the external environment is our sensor data. These various sensors also includes soil moistures and sunlight sensors, which collect they collect data from the external environment. So the collected data from the sensor data, such as soil moisture levels and sunlight intensity, is sent to the control unit for analysis. Okay. And the control unit is the central processing entity that receives sensor data and makes decision based on the data. And it also analyzes the incoming sensor data to determine whether irrigation is needed, and if so, it activates or deactivates the water pump accordingly. Next is under the control unit, here is the water pump control. This process represents the activation or deactivation of the physical water pump based on the decision made by the control unit. And the water pump control process ensures that water is pumped into the irrigation system when needed and based on soil moisture levels. The next is the water pump, the physical pump. This entity represents the physical water pump that delivers water to the irrigation system. Water pump is activated or deactivated based on decisions made by the control unit and user-defined schedules. So the solar panel. The solar panel represents the entity responsible for generating power for the system using the solar panels. So the power generated by the solar panel is monitored and controlled by the power management unit, which is this one. And there's a solar panel. And the power management unit manages the distribution of power generated by solar panel to various components of the system, monitors the power levels, and ensures efficient use of solar generated energy. Notification management here at the mobile app entity under notification management responsible for generating and delivering notifications to users regarding system status, weather conditions, or other relevant information. So, and then users are informed about the system's activity and any potential issues of the notification management or the solar water irrigation. The irrigation schedule management. The irrigation schedule management is same as the notification management entity. So the last entity is the irrigation system control. It controls the physical components of the irrigation system, including the valves, pipes, and the irrigation heads. And also the irrigation system control takes instructions from the control unit and user-defined schedule to ensure proper irrigation. And
So for the circuit diagram, used only for IoT projects. So the solar, it charge the battery, connect to soil moisture to IoT module in the app. So the charge controller, get bulb, microcontroller, and communication module is all in the app. And this is our IoT.
So now for the block diagram, let's start first in the solar panel, which serves as the main source of the energy or power supply. And then from the solar panel, let's go then to relay, which will be turned on by use of the power supply. And then we have the Raspberry Pi that will control the relay, which of course will work by the use of power supply. And then we have the moisture sensor that will check the moisture of the soil. And then the Raspberry Pi will be the one that will control and turns on the moisture sensor. And then after the moisture sensor gathers data from the soil, the data will then go to the Raspberry Pi, and then from Raspberry Pi, it will then go to the mobile application that will be used by the user for the user to check and monitor the watering system. Next, we have the system development.
So for our system development, we have here the 3.3.1 software requirements. The software requirements for the solar-powered water irrigation system integrated with the mobile application prioritize efficiency, functionality, user-friendliness, security, and adaptability. The mobile application interface must be compatible with both Android and iOS platforms, featuring an intuitive design for easy navigation without extensive training. And also, real-time monitoring capabilities are crucial. So displaying key data such as water level and solar power utilization, also scheduling options. Data management involves cloud connectivity for remote data collection, analysis, and retrieval, supported by analytics tools for insight into water usage, ener- energy consumption, and crop performance. And the system integration with irrigation hardware, ensuring seamless control of pumps, valves, and sensors with the added feature of remote control capability through the mobile app. And then the security measures includes data encryption and user authentication protocols to provide an authorized access. Ongoing supports and updates are provided also to assist user with technical issues. This requirement collectively establish a robust and user-friendly system for effective solar-powered water irrigation management in agriculture.
So for the hardware requirements, important hardware parts are required to run a mobile app-powered solar-powered water irrigation system. This consists of an energy generating solar panel system, deep cycle batteries, and charge controllers, and environmental and a soil moisture sensor. Soil monitoring sensors, PLC. So, or microcontrollers are the brain of the system. They control irrigation and handle sensor data. Remote control is made possible by a communication module such as GSM, Wi-Fi, or Bluetooth, and an iOS or Android mobile app. The hardware needs to be resilient to many environmental conditions, long-lasting, and energy efficiency. So next.
So for the testing or the functionality testing is that the functionality testing of the integrated solar-powered water irrigation system with a mobile application encompasses evaluating the efficiency of solar panels, assessing the mobile app interface, gauging irrigation system performance, testing remote access, ensuring data synchronization, examining fault tolerance, validating energy backup, and collecting user feedback. These tests are designed to guarantee the system effectiveness, reliability, user friendliness, and adaptability in various agricultural settings. The focus is on efficient solar energy utilization and remote irrigation management and real-time monitoring through a user-friendly interface, incorporating user feedback to facilitate continuous improvement.
For the usability testing, the usability testing is a method used to evaluate the effectiveness and user experience of a product or system. It involves observing and gathering feedback from real users as they interact with the product, helping to identify usability issues and make informed design decisions for improvement. The usability testing process would begin by defining the objectives and goals specific to the system and app. This could include assessing the ease of use, efficiency, and overall satisfaction of users when interacting with the irrigation system and utilizing the mobile application. The goal of the usability testing would be to identify any usability issues or areas of improvement within the system and app. This could include factors such as the intuitiveness of the user interface, clarity of instructions, ease of navigation, and overall satisfaction with the system functionality.
So we have here our sample prototype for our mobile application. As you can see, the user can check the soil moisture update, which is in percentage and in color code. And then the percentage of water inside the water container. So when the user click the open button, that's the time that the water will flow. And then when the tank becomes empty, there will be a warning, and then there's a 0% that will be shown, and then the user can check also the updated soil moisture in percentage.